Hello calculus students and welcome to the Exam 1 Solutions Guide. I like to do these after the exam to help everybody understand what's going on. I know it's a little bit late, a couple weeks after. I hope it's still useful. Unfortunately, I have the coronavirus, that's why I'm not at school, so I'll have to do everything online, including the recitation session. It took me a while to get this technical setup. I'm doing this weird green screen thing. You can see it's not perfect and it's not actually using a green screen. But yeah, I'm working at that, trying a couple different things. Okay. So in this first video, I would like to go over a bunch of common mistakes or common misconceptions that I observed while grading the exam. And so we'll talk about all those, and then in all the other videos we'll do specific problems one at a time. Since they're all integral problems, which kind of involve like thinking about a lot of possible routes to go and then deciding upon one, they're all kind of like that. So in each of the problems, I think what I'm going to do is just go through the shortest path to a solution first and just show you what it is. And then after that, I'll explain the thought process of what are the different techniques we could have attempted to use on this problem. So just shortest path first, that just, pulled out of thin air, and then I'll explain why did I choose that technique as opposed to a different one. Okay, so let's get started with the common misconceptions, or common mistakes. So first of all, let's talk about the chain rule here. So, personally, I find this notation all over the place to be rather cumbersome, so I like to use just an arrow to mean the derivative. Right, so here I'm saying, recall that the derivative of sine is cosine, and the derivative of x cubed is 3x squared. So remember then, what does that mean about the sine of x cubed? Right, what's the derivative of a function like that? Well, we have to use the chain rule, which says you take the derivative of the outer function like normal, leave the inner one alone, and then multiply by the derivative of x cubed like that. Right? So the derivative of sine cubed is cosine cubed times 3x squared. Now, what that means is, if you see the integral of cosine, right, you probably know that that's sine plus c, right? Because derivative of sine is cosine. It's that simple, right? These two things are opposites of each other, right? So it's tempting to say then that, and same deal, the derivative of the integral of 3x squared is indeed x cubed, and so on. So if you see the integral of cosine of x cubed, it's very tempting to say, oh, well, that's easy. Integral of cosine is sine, so that's just sine of x cubed. But that's wrong. You can see that the derivative of sine of x cubed is not cosine of x cubed. It's cosine of x cubed times 3x squared. So if that times 3x squared is not present, then the integral is not, sine of x cubed. It's not like that. There needs to be a times 3x squared for this to be sine of x cubed. Right? So the chain rule has unfortunate consequences when it comes to integrals. It's that you can't just integrate the outside function by itself if there's stuff going on the inside. This is not legit if that 3x squared is not there. As another example, right, you probably know that the derivative of natural log is 1 over x. So if somebody asks you, what's the integral of 1 over x? Easy peasy, it's the natural log. Now there's some absolute value stuff going on. Don't worry about that. It's kind of just distracting from the point I'm trying to make here. The point I'm trying to make here, right, if somebody asks you what's the integral of 1 over x, and you know that that's natural log, somebody might ask you then, well, what's the integral of 1 over, let's say, the square root of x? Well, it's very tempting to say, oh, well, easy peasy, that's just the natural log of the square root of x. Wrong. Because the natural log of square root of x, right, when you take the derivative, yes, it's 1 over the square root of x, but then times the derivative of square root of x, right? Which would be that. So it's yeah, so it's not as simple as this. Unfortunately, that is not correct. Right, the correct way to figure out that one would be to rewrite it as x to the negative 1/2. And then you use the power rule, right? So that would actually be 2x to the positive 1/2. And so that would be 2 root x. Right, so it does not involve natural log at all. So yeah, so you really got to be careful about this chain rule stuff. Because especially when you're doing it backwards, right? So one more example. People see this and they're like, okay, the square root of t, easy peasy. That's, 2/3 t to the 3/2, right? That was 1/2, so you just use the power rule. That's 2/3 to the 3/2, right? And I know that's correct because if you take the derivative of that, the power comes down by 1, and you multiply the power out front, and those cancel, so you just get the square root of t, right? So that's totally legit. So some people are very tempted when they see one like this. It's the square root of something, right? So no problem. It's just 2/3 that thing to the 3/2. Easy peasy. Wrong. Because when you take the derivative of that, here's how it works out. Yes, the power comes down. Yes, it cancels with the 2/3. Yes, the new power is 1/2. But the chain rule unfortunately says you have to multiply by what's on the inside here. Excuse me, by the derivative of what's on the inside here, which in this case would be 2t. So the derivative of this is not the square root of 1 plus t squared. It's the square root of 1 plus t squared times 2t. And that times 2t makes all the difference, right? It turns out that this integral is not that, right? So yeah. So the chain rule means it's not so simple to do these composed functions backwards, right? Yeah. So that came up a lot. Next thing I want to talk about is distributing. So what do I mean by distributing? I mean distributing multiplication over addition, right? You know how like you can give this one of these, right? Well, let's talk about that with powers. Let's say instead of times 3, we were talking about to the power of 3. Whoops, I don't know why I wrote that. To the power of 3. Can you distribute that over the addition, is the question. No, you cannot. Right? No, you cannot distribute the power over addition. Allow me to show you an example to illustrate. 3 plus 4 is 7, right? Well, check it out. If we square both sides, I will show you that it is not legit to distribute this exponent, right? Check it out. If we distribute the exponent, then that becomes 3 squared plus 4 squared. And you see these things are no longer equal. 9 plus 16 is not equal to 49. So this illustrates that you can't distribute a square over addition. And in fact, in general, you can't distribute any exponent over addition or subtraction. Right? So as another illustration, consider the square root of 169 minus 25. So 169 minus 25 is 144. And I chose these numbers because they're all perfect squares. So check it out. So if we can distribute this square root, if we can distribute this power of 1/2, then that should be the same as that. But it doesn't work because that's 13, that's 5, and that's 12, and 13 minus 5 is not 12. So you see that this step here of distributing the radical or distributing the power of 1/2 over this subtraction was not legit. So yeah, that's something I wanted to mention. Let's talk about distributing powers over multiplication, though, because that does work, which is very nice. For example, 2 times 5 to the third, right? Fortunately, that is totally the same thing as 2 to the third times 5 to the third, right? This is 10 to the third. This is 8. This is 125. And if you calculate those, that's 1,000. And 8 times 125 is also 1,000. And in general, this works. You are allowed to take a power and distribute it over multiplication, right? Not addition, but you can distribute it over multiplication. And in the same way, can't do it over subtraction, but you can do it over division, right? So yeah, so that's a common mistake that I saw people do, is they distribute a power, even a fractional power, across multiple terms, right? Across things that are added or subtracted from each other. That is not correct. You cannot do that. Similarly, let's talk about derivatives for a second, right? If you have the sum of two functions and you want to take the derivative of that, I'll use this notation. The great thing about derivatives is that they distribute over addition. You can just take the derivative of each piece, and that's wonderful. Unfortunately, the same thing can't be said for multiplication, right? As I'm sure you know, this is not correct, right? It is not true that you just take the derivative of each piece. You have to do this somewhat more complicated thing of you take the derivative of one piece, but not the other, and then also the other way around, and then you add those together, right? The product rule, right? Well, in a very similar way, you know, since the derivative distributes over addition and the integral is just the antiderivative, basically, right? They're opposites of each other. Well, the integral of the sum of two functions is exactly equal to the integral of one plus the integral of the other, right? Or if I were to use the antiderivative notation where you just use like a capital letter, right? I could write it like that, right? You just take the derivative of each piece. So let's ask about the integral of the product then. Unfortunately, as you might guess, it's not like that either, right? The derivative does not distribute over a product, over a multiplication, and neither does its opposite, neither does the integral. In order to do the derivative of a product, you have to use the product rule. And in order to do the integral of a product, there is another rule that you have to apply. You can't just do the integral of each piece. You have to use integration by parts, right? I know you've been learning a lot about that. Integration by parts says if you have the product of two functions like we have here, one times the other, you are able to use this formula to kind of swap it out for a new integral, right? So we had this old integral of the product of two things, and we swap it out for a new integral of the product of two things, but the product is a little bit different. We took the blue function, the one we were calling u, and we replaced it with its derivative. Whoops. And we took the green function, the one we were calling dv, and we replaced it with its antiderivative. So we had two things multiplied together. One is now its derivative. The other is now its antiderivative. So it's like we went like this, right? One of them got a derivative, the other one got an antiderivative. And hopefully that's a useful exchange. Sometimes it is, sometimes it isn't. It's up to you, the captain of the ship, to decide if that's a good maneuver to make or not. Often it is not, and that's kind of the challenge of it, is that you have to be prudent in your application of these tools because they're not always the right tool to use. In fact, in this exam in particular, I thought it was rather strange how infrequently integration by parts was the tool to use. I understand you studied it a lot, so I think that may be responsible for its overuse during the exam. A lot of people were using integration by parts when it was not the move. It did not take you in a useful direction. So yeah, that's kind of interesting. And then finally, one last thing that I wanted to talk about is something like this. Let's say you're at this point here. You're at like 5 and 7 or whatever. Here's a common mistake. Actually, hang on. Let me. Well, I kind of can't do that. Yeah, whatever. Here's a common mistake that people made. Is they'd be like, okay, plug in 5 and 7 and then subtract. Boom. Does anybody see what I did wrong there? I hope so. No, the natural log of x between 5 and 7 is that. Natural log of 7 minus natural log of 5. But these things are not the same, right? That says plug in 7 and 5. This says take the antiderivative first and then plug in 7 and 5, right? A lot of people forgot that totally central step of actually taking the antiderivative, right? Of course, it's not that. It's this, right? You have to actually replace natural log of x with its antiderivative. Wait a second, I screwed up. That's not the antiderivative of natural log, that's the derivative, isn't it? The antiderivative is this other thing. Ew, gross. Right, so then that's what you plug in, 7 and 5, right? So 7 natural log of 7 minus 7. 5 natural log of 5 minus 5. Right, so you have to actually replace the original function with its antiderivative, right? Of course, right? But yeah, easy to forget, statistically. So, and then finally, one last thing that I want to say is that, well, you know what? We'll get to that one when we get to it. That's whatever. Okay, all right. That's the introduction on all the FAQ stuff. Let's get into it. Here we go.